Hey everyone, in this video I will cover fundamentals of LLM fine-tuning. So start with different LLM fine-tuning approaches, for example SFT or supervised fine-tuning, and then RLHF or reinforcement learning from human feedback. Also I will cover fundamentals of low rank adaptation, that is LoRa, and setting hyperparameters for regular fine-tuning and also LoRa based fine-tuning. Preparing the right dataset format before you start the actual process of training, and then finally I will go through step-by-step implementing the LLM fine-tuning pipeline on MonsterAPI, which is a super flexible low-code fine-tuning platform. So let's start with the basics. What is LLM fine-tuning? LLM fine-tuning is a process of adapting a pre-trained language model to perform specific tasks with higher precision. While LLMs like GPT are initially trained on vast datasets and excel at understanding and generating human-like text, they often lack specificity for specialized applications. Fine-tuning addresses this limitation by further training these pre-trained models on domain-specific datasets. This process enhances the model's performance in tasks such as sentiment analysis, question answering, and document summarization, etc. on that specific domain. So it's a cost-effective way to leverage state-of-the-art models without building them from scratch. Now let's dive into the different approaches to LLM fine-tuning. We can briefly classify these methods into two categories. One is supervised fine-tuning and other one is reinforcement learning from human feedback, or RLHF. Let's start with supervised fine-tuning. So the first one is transfer learning. This method involves fine-tuning a pre-trained model on a task-specific data. It's particularly useful when you have limited task-specific data, as it reduces the amount of data and training time required. Then multitask learning. So in multitask learning, we fine-tune the model on multiple related tasks simultaneously. By leveraging the commonalities and differences across these tasks, the model develops a more robust understanding of the data. This approach improves performance, especially when tasks are closely related or data is limited for individual tasks. And then we also have the very popular few-shot learning. So in few-shot learning, it enables the model to adapt to new tasks with minimal task-specific data. By providing a few examples only during inference, the model leverages its vast pre-trained knowledge to learn effectively from limited data. This method is beneficial when labeled data is very less or is very expensive, and it can also be integrated with reinforcement learning from human feedback, or that is RLHF. And finally, we also have task-specific fine-tuning, where we fine-tune the model to the nuances of a particular task, optimizing its performance for that specific domain. Task-specific fine-tuning ensures the model excels in generating precise and accurate task-specific content. So as you can probably understand that it has some similarities with transfer learning, but task-specific fine-tuning focuses more on adapting the model to the exact requirements of the new task. Alright, so all these methods were under SFT, that is supervised fine-tuning. And then the other fine-tuning we have is RLHF, that is reinforcement learning under human feedback. And basically, it's of course a very deep topic, but there are mainly three steps under RLHF, and they are: number one, supervised fine-tuning, then reward model training, and then reinforcement learning. And these three-step processes go in a sequential basis. So the first step is SFT. This involves conventional fine-tuning, where prompts such as questions are matched with their expected outputs like answers. And then reward model fine-tuning. This step entails training a model to produce a scalar reward when given a prompt and set a ranked outputs. Generally, the dataset for this involves pairs of prompts with one correct and one incorrect output. The purpose of the reward model is to give feedback to the model trained at the next step. And the next step is, that is the third step, is reinforcement learning. In this phase, the model fine-tuned in the first step, that is under the SFT, generates an output for a given prompt, which is then scored by the reward model from the second step. The RL process, that is a reinforcement process, uses this reward to enhance the generation performance. Now, during the fine-tuning process, the most important challenge that everybody faces is about compute resources, because full fine-tuning, that is full precision fine-tuning, involves adjusting all the model weights, which can be time-consuming due to the need to compute gradients across all weights to minimize the loss between the actual and the generated outputs. This process involves billions of floating point computations and constant data movement within the GPU memory hierarchy. And the most popular solution to this challenge is LoRa, that is low rank adaptation. First, what is LoRa and how does it work? So as I explained earlier, when we fine-tune a language model, we modify the underlying parameters of the model. The core idea behind LoRa is to model this update to the model's parameter with low rank decomposition implemented in practice as a pair of linear projections. So LoRa modifies the self-attention and feed-forward layers of a transformer model by introducing low rank matrices. This adaptation significantly reduces the number of trainable parameters during fine-tuning. This means that instead of updating the large, dense weight matrices, only the smaller low-rank matrices are trained and updated. This reduces the amount of memory and compute resources needed, since the low-rank matrices have significantly fewer parameters than the original dense matrices. Now let's quickly understand the mathematics underlying the LoRa concept. It's actually a very simple idea, but has such a huge impact throughout the AI industry. So in LoRa, the changes in the original weight matrix W is adapted by adding a low-rank product of two smaller matrices, A and B, where A and B are the low-rank matrices. So the adapted weight matrix becomes W plus AB. And these matrices are the core components of LoRa's adaptation mechanism. They are much smaller compared to the original weight and directly influence how the original weights are adapted during training. So the actual mathematical expression of LoRa is given in this equation, where the weight W dash can be represented as equal to W underscore 0 plus delta W, and delta W, and that whole expression is again equal to W underscore 0 plus AB. So W underscore 0 remains static during the fine-tuning process and the underlying parameters are being trained. The matrix A is initialized with uniform Kyming distribution, where B is initially set to 0, resulting in delta W equal to the product of AB being 0 at the start of the training. And when fine-tuning with LoRa, the original weight W are frozen, and only the elements of the low-rank matrices B and A are trained, leading to a drastic reduction in the trainable parameter count. And overall, the benefits of LoRa are multifold. It has been proven again and again in many studies. Number one is that a single pre-trained model can be shared by several much smaller LoRa modules that adapt it to solve different tasks. Then number two, LoRa modules can be baked in to the weights of a pre-trained model to avoid extra inference latency, and we can quickly switch between different LoRa modules to solve different tasks, that is hot swapping. And then we only have to maintain the optimizer state for a very small number of parameters, which significantly reduces memory overhead. Alright, now let's see the power of LoRa with a very simple example. And although the example is simple, this is exactly what happens when you implement LoRa into your fine-tuning project. Let's say you have two metrics, 1000 by 1000. That is, when you multiply them, which is what you have to do for training, you get a weight matrix of size 1 million. That means you have 1 million parameters, and that's how many parameters you have to train if you don't bring in LoRa. But then with LoRa, instead of doing backpropagation and modifying all the 1 million weights, we determine a low rank. Let's say we determine the low rank to be this number 5. Hence, with LoRa, we will be introducing two smaller matrices, A and B. This A and B will be 1000 by 5 and 5 by 1000. And how I am arriving about these particular numbers and calculation, that is a simple matrix mathematics. You can just Google search and get to know how you arrive at this matrix calculation when you have a low rank. So now with LoRa, instead of modifying the original 1 million weights, we will only update the weights in matrices A and B during training, which totals 10,000. And how it is 10,000? Because you got 5,000 here and 5,000 here, and you add them together, you get 10,000, which is just 0.01% of the initial weights. And despite updating only a tiny fraction of the weights, this approach can still capture significant information and lead to effective fine-tuning. This is because the low-rank matrices A and B are able to interact with the entire space of the original weight matrix. And we will see in a moment that when we do LoRa-based fine-tuning, we have to choose this low-rank number, that is number 5 here. And this is actually an hyperparameter, and you have to choose very carefully this rank number, because choosing a smaller rank can save a lot of parameters and memory and achieve faster training. However, a smaller rank can potentially decrease task-specific information captured in the low-rank matrices. On the other hand, a larger rank can lead to overfitting. Hence, it's very important to experiment in order to achieve the ideal accuracy performance trade-off for your specific task data. And continuing with the rank parameter discussion, the next topic that I want to talk about is all the hyperparameters that you normally need to set during your fine-tuning process. So right now, in the screen, you can see this is taken from the training arguments class of Hugging Face, in case you are doing the fine-tuning completely based on a transformer library of Hugging Face. These are some of the standard hyperparameters that you have to set. And of course, these are only few. There are so many more. You can just take a look at the Hugging Face documentation to check all about them. And coming back to the very first one is batch size. This is probably the most common hyperparameter that you will start with. So basically, small batch sizes require less memory during training, but lead to more noisy model updates. And just like a regular deep learning job, the batch size is a trade-off and hyperparameter to experiment with when training your language models. Next one is learning rate, LR. The learning rate is a crucial hyperparameter for any model, including the language model. And normally the conservative approach is to start with a very low learning rate and use a cosine schedule with a 0.1 warm-up ratio, and then gradually you can experiment with it as your training progress goes ahead, and depending on the log, what kind of result you are getting, you can change this one. And the next one is number of epochs. For fine-tuning LLMs, it's suggested to start with 3 epochs. This number can be adjusted based on the specific needs of the model and the data it's being trained on. And then you have LR sensitivity or learning rate sensitivity. That is, fine-tuning is more robust to learning rate changes than parameter-efficient methods like LoRa. And therefore, it's important to tune the learning rate carefully to achieve the best performance. And LR sensitivity determines exactly that. And then you have got gradient clipping. That is, apply the gradient clipping to limit the magnitude of gradients during the backpropagation. This prevents exploding gradients and stabilize the training process. And max output token typically means that the higher you set the max output tokens, the more coherent and contextually relevant the model's response will be. Subsequently, in contrast, setting a lower max token limit requires less processing power and memory, but in potentially not providing the model with sufficient room to craft the optimal response. So you leave the door open for incoherent errors when you set a very low max output token. And then you have the famous top K and top P sampling parameters. So these two hyperparameters are very related, and they provide helpful ways to control the balance between diversity, coherence, and adventurousness in the model's output. First, starting with top K parameter. So this is an integer between 1 to 100 with a default value of 50. And this one limits the model to considering only the K most likely next tokens at each step. So a higher K value allows for more diverse and unexpected outputs, while a lower K value constrains the model to safer, more probable choices. And then the top P parameter, this is a decimal number in the range from 0.0 to 1.0, and it selects from the smallest set of next tokens whose cumulative probability exceeds a threshold P. This allows for dynamic adjustment of the candidate pool based on shape of the probability distribution. And the very related hyperparameters with top K and top P is the temperature hyperparameter. That's a very popular and very frequently used hyperparam. So basically, the temperature parameter will control will give you the control to change the range of possible output tokens and influence the model's creativity. So a temperature of 1 has no effect. The model will generate tokens based on its original distribution. As the temperature approaches 0, the model becomes more deterministic and is more likely to pick the most probable token. Conversely, as the temperature increases, token selection becomes more uniform and random. And here is a rule of thumb for using the temperature parameter and also the top K and top P parameters. And mostly these three parameters you will be using in combination together because they affect each other and they are very, very related. So the rule of thumb is high temperature values can produce more diverse but sometimes nonsensical outputs. Low temperature values can make the output very deterministic, sometimes overly repetitive. And top K can ensure a baseline level of quality by eliminating rare tokens but can be restrictive. And top P can adapt to the context and potentially produce more nuanced outputs but might occasionally include rarer tokens if the model's confidence is split among many tokens. Alright, now the next important topic is preparing your dataset before actually starting the training. And this is kind of the most important job in the pipeline, you can say. So the first one, the plan is to show you three different dataset format. One is instruction dataset, and then a DPO dataset, that is direct preference optimization, and then the third one is a ORPO dataset. So right now, ORPO means odds ratio preference optimization. Because in most of your regular fine-tuning job, these are the different structure that you are going to see. And the first one is this instruction dataset. This is probably the most common form that you will be seeing in actual job. So here in this function, this is formatting a prompt function util, very simple function. It is processing data entries from a dataset, each containing three fields: instruction, input, and output. It formats these three fields, that is instruction, input, and response, into a particular format. And that format is defined here, alpaca prompt. So it formats these fields into a template string stored in this variable alpaca prompt and appends an EOS token to each formatted string. Because the EOS token is necessary for indicating the end of sequence in a model that require a clear delimitation of input, which is the case for most of the language models. And for the next dataset, that is the DPO, this is an example format for the direct preference optimization dataset. So we need here an instruction and two possible responses to that instruction. One response is chosen, which is what you see here in this column. It is a valid and ideal response to the instruction. And the other response is rejected, that is, it is not an ideal response, that is this column. So this is just an example dataset that I have taken from this particular name, DPO Mix 7K Simplified. And just to show you an example of a DPO dataset. And the structure of the dataset is straightforward. Basically, for each row, there is one chosen answer and one rejected answer. The goal of DPO training, that is RLH, reinforcement learning with human feedback training, is to guide the model to output the preferred answer. The model will be trained to directly optimize the preference for which sentence is the most relevant given two sentences. So we can create a DPO dataset synthetically as well based on existing dataset. And the common strategy for creating a synthetic dataset is that you already have an instruction and response pairs and then generate an extra response. So if you combine this strategy with another model as a judge, you can evaluate your two responses and take the best response as your chosen one and the worst as your rejected. And that strategy depends on a judge model of sufficient quality to evaluate the response. Up until recently, the only option was GPT-4, but with Prometheus 2 and few other models, we can now use an open source model to do the evaluation, in giving us a completely open source distillation pipeline. So to synthetically create DPO dataset for a set of prompts, you can create the answer with GPT-4 Omni model, which will be your preferred answer, and with maybe Llama-3.1 or similar class of models to create your rejected response. And based on these dataset structure, that is instruction, chosen, and rejected, you have a very simple util method right here that you will mostly see during your DPO training. That is, we'll take a dataset ID, which will be a Hugging Face dataset ID is most normally. And then you just define a quick map function here to get from each of the samples, that is each of the row of the dataset, you get the prompt, chosen, and rejected column values. And then apply this map function on your dataset, which is what is returned from this entire util method. So it's pretty simple. And the third dataset type is for ORPO training, that is odds ratio preference optimization. And basically the structure almost remains the same for DPO training. That is, you have 3 columns that is necessary: the prompt, which is your instruction, and that is this column right here. And you also need a preferred response and a rejected response, just like in DPO. And also to mention that when you'll be seeing using Monster Tuner to implement an end-to-end fine-tuning pipeline. And Monster Tuner from MonsterAPI, they provide a text area while you are setting up your fine-tuning job, where you are creating or you are allocating for different kind of dataset structure. And there you can select and edit your column names, etc. Because in some dataset, these column names will be slightly different. So the Monster Tuner platform gives you enough flexibility to change all of them. So no worries, just to mention here. All right, with that, I come to MonsterAPI's website. Here is where we are going to do the fine-tuning job today. So MonsterAPI is a new service from MonsterAPI designed to streamline fine-tuning of popular AI models. Pretty much they support all the open source models here on their platform. And they have got advanced GPU computing infrastructure. You have many options to select many GPUs. And of course, it is a no-code platform and also a low-code platform. So that means if you do not want to write any code, you can just get started within minutes by just selecting few of the configuration for your LLM fine-tuning. So once you sign up, you will get some free credits to do your experimentation, and that's kind of enough to get you comfortable with the whole platform. And this is right here, their FAQ page. I'm looking at few of the common question. So who is the solution for developers, content creators, researchers, etc. Technical details, what language models are supported. Our platform supports a range of popular language models, including Code Llama, Llama 2, GPT-J. Okay, these are actually quite, they have said which were there anyway. So they support pretty much all the recent models, and Llama-3.1 was recently released, and they supported it within 30 to 36 hours. So they very much completely updated their platform with the latest models. And otherwise, they automatically configure GPU computing environment for you, which is optimized for higher throughput, because in the backend they use the package VLLM, which is one of the most popular tool in the industry for inferencing, and MonsterAPI uses that for their inferencing. And beyond these, they take care of very much all the configuration for your inferencing and fine-tuning pipeline. For example, optimizes the memory usage by finding the optimal batch size, auto-configures flash attention to or SDPA for faster processing with reduced memory consumption, and comes integrated with the Onslaught library for up to 2x faster processing on supported models, and integrates experiment tracking with 1dB and automatically pushing to Hugging Face Hub. Also auto-configures a pipeline to complete without any errors on their cost-optimized GPU cloud. And all these benefits that I just mentioned, they are taken care of without you writing a single line of code. That's pretty amazing. All right, now let's get started. And once you sign up, you will come to this initial page, which is a dashboard actually. And from here, you can see that you can deploy, you can fine-tune. For example, if you click on deploy, these are some of the most common one, which with the ready-made recipes. Otherwise, definitely you can bring in your own model, that is your own local model, back into MonsterAPI to be served and do inference with MonsterAPI. That's the whole idea. And once you click on the fine-tuning section heading right here, you will see that you can do fine-tuning with all the different kinds of models. So complete multimodality is supported here. Whisper for your audio fine-tuning, SDXL for your diffusion fine-tuning, and this is for language fine-tuning. All right, so now I'm in the language fine-tuning part and just going to create a new fine-tune an LLM. And right here, you just mention, today I'm going to test Llama-3.1 and model name. Here you will see all the models, everything is pretty much supported here, all the open source model. And let's look for Llama 3.1. You can actually type here. So 3.1. Yep. So they already support 3.1 8B base and 8B instruct and also the 70B version. But the 405B one is coming very soon. I got to know from their announcement that it's coming very soon, probably within a couple of days. So for now, I'm just going to choose the instruct one. Next step. Task type is because I have chosen instruction fine-tuning, and as I discussed in the initial part of the video, we can do instruction fine-tuning or DPO fine-tuning or ORPO fine-tuning, but this is going to be an instruction fine-tuning. Let's choose that. Dataset source. Here you can actually bring in your own dataset, and for that you just need to choose accordingly, but otherwise you can choose any of the Hugging Face dataset. You can directly get the name of the Hugging Face dataset, put it here, and it will come up. So if you want to upload your own dataset from your local machine or cloud, just choose custom dataset, and then here upload and use your own dataset for fine tuning. So you can actually upload your dataset. But in this purpose here today, I'm just going to choose Hugging Face dataset and select HF dataset. Let's choose the alpaca one because that's the most popular. Okay, and choose a subset default. Yeah, because if the dataset had trend, test, validation, etc. split, then we could choose here. But in this case, I'm just going to choose default because I think they don't have any split like that. But I'm going to check it in a second. And then do you have a LoRa adapter to deploy? So in case you have an adapter, you can just switch on and then put your checkpoint right here. So this is just some really awesome, really helpful configuration because now most of the times you may need to do a LoRa based training where you already have a checkpoint for your adapter. Then just put the checkpoint here and it will be automatically integrated with your fine-tuning pipeline. And so this dataset that I was just talking about that we chose for this fine-tuning is this one, TatsuLab Alpaca. And as you can see, this is a very popular dataset with a download last month of 91,000 plus and very reasonable size as well, 24.2 MB. And so this is a dataset format. It's an instruction fine-tuning dataset. So you have an instruction column, output column, and text column. We pretty much need the instruction, which represent the prompt, and the output, that is a response. And as you can see, we have a total 52,000 rows within the train segment. And there is no other segment here. And that is why we were not getting any option to choose a train test or valid in our MonsterAPI configuration. And coming back to the configuration page here, just one thing I wanted to show you here, that this part where it says prompt configuration. So the idea here that you have to have a proper column heading name during the training. And so you need to be able to customize the column heading right here based on your dataset. But in this case, it is grayed out because I have chosen a default dataset from Hugging Face. So it already knows, the MonsterAPI's all internal configurations already knows what is the right column heading. That is a prompt configuration in this case. But in case you choose your custom dataset, let's choose one. So choose a custom dataset. Immediately you see that this area become activated. You can now change it. So just like it says instruction, replace with instruction column name. So in case you had instruction column name of response, because that's the most common one representing instruction, you can just put the whole thing here as response, like that. And so that your training pipeline will automatically be changed internally to take care of the column heading name accordingly. So in this case, I'm just proceeding ahead to the next step. And right here, you can see all the regular hyperparameters that we talked about in the initial part of the video are here. You can change it depending on what you want. So we have epochs, context window, early stopping, patience, learning rate, everything. I'm not explaining them again and again because we already talked about in detail earlier. And of course, you can also track your fine-tuning job with 1DB. So all you need to do, just put your 1DB token or key here, and all the log will be automatically sent to 1DB, and you can see all the log reports right from here. And also, after the fine-tuning is done, you can upload the fine-tuned weights directly to Hugging Face. So you don't have to separately manually upload your Hugging Face repository after you fine-tune. Just put your Hugging Face key here, and it will automatically be uploaded. And let's look at the advanced setting. These are some other hyperparameters for your fine-tuning. So we have LoRa alpha, gradient accumulation steps, LoRa R, which is a rank parameter that we discussed in detail earlier, LoRa dropout. Everything is configurable. You can choose whatever you want depending on your case. And definitely when you're fine-tuning, do experiment with different values so you ultimately come to the most optimized one. So for now, I'm just going ahead. And here you are. You can see the actual fine-tuning is just going to start. So this is the final overview page that will give you all the statistics, all the parameters that you have set till now before you start the actual fine-tuning. So job name, Llama-3.1 model this is what we chose, instruction fine-tuning, dataset, everything. And now here it's showing all the advanced settings, all the hyperparameters, an estimated cost of 40 to 60 credit per minute. So remember these, that once you click here, create job right here, it will take maybe a couple of minutes to provision the machine, etc. in the cloud. So during that time, there is no consumption of your credit. Only when the actual fine-tuning job is started, then your credit will be consumed. Let's start it. Yeah, validating and submitting. And while it is allocating the machine for you, let's quickly look at the pricing page here. So they have two plans, Wolf plan and Beast. Under the Beast plan, you get these 35,000 credit up to 10,000 daily API calls, 7,000 image generation, etc. And under the Wolf plan, that's a smaller number of credits. And let's see the Monster plan. Yep, that's 50,000 credit up to 20,000 daily API calls. And coming back to the dashboard, I can see that the job that we just started, that's now showing as in queue. That means it is just allocating the machine. So you can just click on this icon here to check all the details anytime. That's my all the hyperparameters, that the deployment name, etc. Yeah, so and 1db I have not set, so that's why it is showing use 1db as false. All right, when it is in the queue, let's quickly look at their documentation, because they have a very beautifully written, very exhaustive step-by-step documentation, and also lots of blog actually mentioning step-by-step the usage of the platform for fine-tuning, SDXL fine-tuning or deployment, etc. Lot of collab notebooks showing deployment, actual deployment codes, etc. For using with MonsterAPI. Remember that MonsterAPI's technology stack is very exhaustive, very advanced, because it incorporates several cutting-edge latest techniques and tools designed to optimize the performance and efficiency of your fine-tuning and inferencing. For example, Flash Attention 2, they supported this advanced attention mechanism enhances the model performance by significantly reducing memory usage and computation time, allowing for faster and more efficient processing. They also support auto batch size, which this feature automatically adjusts the batch sizes to optimize memory utilization, ensuring that the available hardware resources are used efficiently and effectively during model training and inference. Also, data validation API, they have this a particular feature which ensures that datasets are correctly formatted and validated before use, reducing errors and improving the quality and reliability of the training data. And for inferencing and deployment, they support VLLM in the backend. So as probably you know, this is the most popular tool for inferencing and fast throughput, because they use a paged attention. And VLLM has been widely adopted across the industry actually, with huge number of GitHub stars and more than 350 or so contributors worldwide. So VLLM enables high throughput serving of large language models, facilitating quick and efficient deployment of these models for your downstream application. The main specialty of VLLM is that whenever you need fast throughput, then VLLM is your go-to tool. So in their documentation, I just came to this part, projects using MonsterAPI. Just to show you all the different projects that you can do with the tool. So here, Auto Blogger with MonsterAPI, Zephyr LLM with RAG for medical queries. And these are actually supported with the full Google Colab code if it is applicable. For example, you can see the Colab demo link right here. And for many of them, they have a blog, completely written blog as well. So they are putting a lot of effort on helping you to use their platform. So coming back to their API reference tab right here, I like this statement. If building an AI-powered application is like navigating a jungle, then MonsterAPI is your Swiss Army knife. And I very much agree with them, because they will help you in every cycle of your inferencing and fine-tuning pipeline. So right now I'm looking at API inferencing page. Remember that when you fine-tune a model, then you can serve the model as a private API endpoint using MonsterAPI as a tool. So that means that you can have it integrated to your apps, whether mobile apps or web apps, and that model and the intelligence and the token generation, everything will be served by MonsterAPI after you are fine-tuned or done with your fine-tuned model. For example, take a look at here, that is some of the features of their APIs. And if you are a developer and trying to integrate the text generation from a large language model into your downstream task or downstream applications, that you would know the importance of JSON-enabled output. And that's exactly what responses are supported by the MonsterAPI. So requests can be processed with either form data or JSON encoded bodies, and responses are returned in a JSON encoded format. This is really, really, really useful, and utilizes industry standard HTTP methods, response codes, and authentication procedures. Obviously, that's all looks good. And here I'm looking at their blog page in their site, and there are so many of them, quite lengthy blogs on each part of their platform. So using their platform should be very easy. And so right now I'm in the fine-tune a large language model part of the documentation. Just to give you the context, we already saw the process and steps of using their platform directly without writing a single line of code to launch the fine-tuning of Llama 3.1. But here, these examples and these documentation is for using their Python client. So they have a MonsterAPI package, Python package, which is the Python client for using the Monster Tuner platform right from a Google Colab notebook or any Jupyter notebook or anywhere right into your Python file, right? And these are some of the examples they have given in the documentation, and these are some of the curated list of models we support for fine-tuning. But I think these are not the exhaustive list, because we already saw that Llama 3.1 is not listed here. So I think they just need to update the documentation here because they support all the latest models. So right now, I'm going to take you through a quick Google Colab for using their Python client to do the same fine-tuning. All right, I'm in Google Colab, and this is using the MonsterAPI, this particular package, which is a Python client, to be integrated into your Jupyter notebook to do the fine-tuning. So just install it first with pip install, and then just bring it into your imported packages, and then launch your fine-tuning job. So overall, it's a very short Google Colab. As you can see that I'm just defining these cells indeed, and that's pretty much it, only few lines of code. So what these cells are doing, let's go through it. So this code block below sets up the launch payload for fine-tuning an LLM using specific configuration. The payload includes model path, LoRa parameters, data source details. Yeah, obviously you can see this is doing on Mistral 7B. And then defining all the LoRa related configuration, etc. If you are using LoRa or quantization or PEFT, these are all the standard hyperparameters that you have to define. We discussed about these in the early portion of the video, and you can also check out their definition in either Monster documentation or in Hugging Face transformer libraries documentation as well, because they are exactly the same. And one thing to note is here that in this particular example, we have given these use quantization equal to false. So that parameter has been set to false, means that you are not using the quantization. But if you are planning to use quantization, and then definitely switch it back to true. So basically, you know that with quantization switched on, you will be reducing the precision of the numbers used to represent model weights. For instance, instead of storing weights as 32-bit floating point, you might store them using just 8-bit or 4-bit, and this significant reduction in data size means the model requires less memory and computations can be executed much more faster. So once you define your entire launch payload, everything very much is defined right here, and then you just apply it. That is client.finetune service equal to LLM and params, and there goes your entire launch payload right here. And also you can get your deployment ID with this code. And once your fine-tuning job has actually started, it is very important to monitor the various status. So here are some of the ways that you can monitor them. So first, get deployment status. You use this client.get deployment status method and pass your deployment ID. That will show you all the status. And talking about status, I just came back to their documentation job status part. And the job can have 4 status: launching, in progress, completed, and failed. When the job is in progress, after launching, it typically takes 4 to 5 minutes for the job to enter the in progress state. During this phase, you can view the job logs by selecting view jobs, etc. So when the job has been completed, on the job completion, the download option becomes available under select and action. Yeah, so basically, I think during the launching status, there is no credit consumption. Only when it's in progress, then your credits will be consumed. Okay, so coming back to the model, to the collab. So yeah, after your job is finished, definitely don't forget to terminate the job. Otherwise, it will continue to consume your credit. And for the termination, you can just run this method: client.terminate deployments and pass your deployment ID. So these are all the methods: terminate deployment, then get deployment logs, get deployment status. All these are coming from these Monster API Python client that we installed. And of course, the definition and details of these methods are in their documentation. And now coming back to the dashboard, which is where we started our Llama 3.1's fine-tuning. Let's take a look. So right now it was in the queue, but now the queue is empty because it has started the training, and that's why it is showing under in progress. And you can check the details by clicking these icon here, view job info. Yeah, so these are my details, and we can see again all the parameters here, right? And the credit, some credit has been consumed already. And this is my deployment ID. You can get the deployment ID from here as well. Just copy it. And yeah, so that's pretty much it for this video. So definitely check out their site and do sign up, because after sign up, I think you will get 2,500 credit, which is pretty much enough for all your basic experimentation. And yeah, they have a lot of resources under this section. All the models they support here. You can do some interesting fine-tuning with your SDXL model, standard diffusion. And before ending, I just want to show you this part of their site as well. This is Monster GPT. This is actually a custom GPT where you can fine-tune an entire model by talking in your ChatGPT interface. And this is the official page from where you can launch your these custom GPT by just clicking here, try Monster GPT. And you can achieve everything from here. For example, checking the status of your fine-tuned model when it is getting fine-tuned, and also terminating it, the entire life cycle of a fine-tuning very much. And then after fine-tuning is done, you can deploy the fine-tuned model right from ChatGPT. And of course, the ChatGPT will authorize your credentials by asking for your email, etc. And the authorization will happen in the backend. So it's pretty amazing things, but I have got separate video on this particular facility. So I'm not talking much more on this right now here.